Recording is rolling. Welcome to Friday, October 22nd. You guys picked up your centrifugal force and gravity quiz. You guys got that? And we are just going to go through as many of these puzzles as we can, which is probably just going to be the chapter 10 ones, Energy Work Simple Machines. And then chapter 11, Conservation of Energy. Well, I'll save those for next week, so pretty good split. That is the plan. Decide. So first one, number 52. Got the third floor of a house is so many meters above street level. How much work is needed to move a refrigerator of this mass up to that height? Okay. So fridge of some mass, move it some height, how much work? Okay. So you guys remember from last few days, we have all these energy terms. Work is like an energy transfer. We can basically treat it like one of these terms. Okay. Force times distance. Okay. So you push with some force times some distance. Now this is a dot product, which means that everything has to be lined up like the same direction. But that's not going to be an issue for the fridge because we're lifting the fridge straight up and it's moving straight up. So, all right, sounds pretty good. Number 52. Hey. Let me draw a quick free body diagram. So you got this fridge. It's going to have a weight down, that may be mg, and there'll be a lifting force, F sub lift. Right? And wouldn't it be the case that you would need to apply a lifting force that was equal to the weight, maybe if you're lifting it at constant velocity? Right? That's what that free body diagram might be referring to. Might be referring to a constant velocity situation, like move it straight up. And we're lifting this thing some height. So h, something like that too. Okay. Well, we need some numbers. Notice I told you the mass of this fridge, not actually the weight, right? So mass, now I'm going to make up my own mass number. Let's say it's 200 kilograms. Okay? So like I normally do, I normally change the book numbers a little bit, but same story otherwise. And I'm going to move this up, 11 meters. That's what I'm doing. How much work would be required to do that? Let's say, how much energy would you have to expend? Maybe you have a machine and you're trying to lift the fridge. How much energy? Right? So work is equal to force times distance. Okay? The force is upward, the height changes upward. So the cosine of 0 is just 100%, just 1. Okay, so no trigonometry issues. Hey, the force applied. See this free body diagram? It gives away that that's equivalent to the weight. Okay? And the distance you move it, well, that's the height change. Oh, look at that. MGH. What is MGH again? What kind of energy? Potential energy. I mean, this makes sense too, right? The work you put into lifting it is equal to the potential energy that it ends up with. Okay, so I've got a 200 kilogram fridge. Don't forget that you're in Earth gravity. That was implied, right? Like your book did not spell out to you that was the case, but you'd have to remember that. And then the height change is so many meters. You guys in your notes also remember that the mass of the fridge is not the weight of the fridge, right? Okay. Weight is equal to mass times gravity. Okay. So I've got a 2,000 Newton weight fridge moving up 11 meters. That looks like 22,000. 22,000 what? What's the unit? Joules. Good call. Joules of energy expended lifting that fridge. Okay. You might also call that 22 what? 22. What's the prefix for a factor of 1,000? If you have 1,000 meters, you have 1 kilometer, like k kilo. Okay. 22 kilojoules. It'd be the same thing, wouldn't it? Okay. Get there? At number 66. Oh, yeah. At number 66, sled. Diego pulls a sled with this mass across a level snow with a force of this many newtons on a rope this many degrees above the horizontal, exactly as shown in the picture. So that first sentence, well, just summarizes this picture, if you like the picture version. If the sled moves a distance of this many meters, horizontally. How much work did Diego do pulling that sled? So that picture, and then if you add to that picture the distance it moves, then you can figure this out. So 66. I'm going to make up my own sled. It's going to have a little bit different mass and whatnot. Okay. So got a ground, get a sled. Now my sled is going to have a mass of, let me see what they did. I'll call it 5 kilograms. So pretty close to the book number. This guy's pulling with some force, like a force. So the pulling force is, I'll call it an even 300 newtons, and so many degrees above the horizontal. Maybe I'll do a 20-degree angle above the horizontal, something like that. And there's one other number you have to know the energy transfer, and that's, well, what distance to actually pull it for. Because if it's a really short distance, probably not a whole lot of energy. If he's pulling it for like miles and miles, ooh, that's a big old task right there. So the distance move is, I'll call it 100 meters. Okay, so a football field from end zone to end zone, that's 100 yards. A meter's a little bit more than a yard, so think about length of the football field. All right. So what is the work done moving this thing? Well, that's going to be your force times distance, just like for the fridge. Okay? And see, this is a dot product, so you need everything to be in the same direction. Oh, so do you guys remember, as a definition, I told you this is the same thing as FD times cosine theta, right? If you want to stick to that definition, it'll definitely get to the right answer. But I actually prefer myself to dig into like why that would be, right, on a case-by-case basis, which is actually going to save you in the one of these upcoming problems, right? Because there's like a tricky angle that, well, not this one, but shortly. So this 200 Newton force, or sorry, this 300 Newton force, I should say, right? It's up and to the right, which is partly up and partly to the right, which might make you think, hey, there's components that are involved. And only one of those components is actually in the direction of motion. The other one is like partly lifting the sled from the ground and maybe alleviating some of the normal force, but only this component. What component is this? The sine or cosine component of 20 degrees? Cosine, yeah. Isn't this equal to 300 newtons times cosine of 20 degrees? Right. That's the only component of the force that's actually moving the sled forward. That's the only component that's doing any work. Right? One of the first things you learned in this class, and before you did kinematic motion, it taught you guys how to break vectors into components. Right? There's this other vector here too, but 300 newtons times sine of 20 degrees, but that's not really going to be relevant to this question. Right? So I'm going to say that the only force that actually does anything is 300 newtons times cosine of 20 degrees. Okay. And it does that for the full 100-meter distance. Okay, is that? Okay. Now, whether you did the full force 300 newtons times the full distance 100 meters and then times the cosine after the fact, or if you did it like I did, where I find the component and then multiply it, yes, it's going to be the same thing because multiplication is commutative, so you can multiply anything in any order, but I think of it this way. Right, how much energy is involved? So 300 newtons times cosine of 20 degrees, right, all times 100 meters. I'm looking at 28,000 some joules of energy. Hey, this 91 on the end. If I was given these numbers, like that number is significant figures, is the 191 significant? No, I don't actually know that precision. It's just showed up on the calculator. Might be more accurate to call this 28 kilojoules. That might be actually be a better answer in terms of sig figs. Okay? Or if you stuck to scientific notation, you might even call it 2.8 times 10 to the 4 joules. Okay, so there's 3 different ways to write the answer. Okay? And the bottom 2 ways are actually, strictly speaking, a more correct way to do that. Okay? Right, now, that energy put into the sled, there's some possibilities of what this means, depending on other information that they did not give to us. So if there was friction going against the sled, which there probably was, right? And maybe the sled was going constant speed, then that friction force would be balancing this force but backwards, and so no net work was done on the sled. There was positive work done by the guy pulling it and negative work done by the friction, and it all washes out. Right? Or if you want to get crazy with this, what if he was actually pulling it across an air hockey table? If that was true, if there's no friction, do you think that this sled is speeding up faster, faster, faster? It's got to be. Right? How fast would it be going at the end? Well, this work would all go into what kind of energy? Not potential. I don't see any hills. Kinetic, all into its motion. You could set this equal to 1/2 mv squared and solve for the final speed if it was an air hockey table. Right? But sort of a side thought there. Right, number 67, escalator. So Sao Long has a mass of so many kilograms. She rides up the escalator at Ocean Park in Hong Kong. Sounds fun. This is the world's longest escalator, with a length of, wow, look at that, over 200 meters, and an average inclination of about 31 degrees. How much work did the escalator do lifting her up? Right? I mean, I'm sure that escalator is hooked up to an electric grid, and there's electricity running through it, and somebody's got to pay the power plant. Right? So how much energy was purchased in doing that lift? So 67. Let's get ground level. Let's get an escalator going. Escalator. Something like that. Start here, round this thing up. Okay, so I'll change the numbers a little bit. I'm going to give her a mass of 60 kilograms. I'm going to say this length. I'll just round it to 200 meters. Okay. And let's say this angle of incline is 30 degrees from the horizontal. Right. So how much work to lift her up? Right. Right. So you guys know that work is the dot product of force and distance, so force times distance. Okay. And okay, now here's where things get a little funny. You guys know the dot product of force and distance. You guys know that the weight is straight down, so to lift her against gravity, that'd be something to do with vertical, like straight up. But the distance, this length, well, that's on an angle. So there's going to be maybe some trigonometry component to this. And the book definition is F times D times cosine theta, right? So here's where you got to be really careful, is that that cosine of theta, that theta is defined as the angle between the two vectors, right? So if she's being pulled up against gravity, or gravity is pulling vertically, so this force is something to do with vertical, right? Okay, you have to hoist her up. Okay. And the distance is on this angle. This angle, this 30-degree angle, guys, is that relative to gravity or is that relative to the horizontal? That's relative to the horizontal, isn't it? So if you did FD cosine theta and use that as your theta, you would actually get the answer wrong. Okay. How about this? Okay. What's this angle up here? This is a 30, 60, 90 triangle. Oops, I gave away the answer. Wouldn't that be 60 degrees? Right? Okay. Actually, wouldn't that be the angle between the two vectors, like this distance vector and something to do with like gravity being vertical? Ooh, maybe that's the angle we actually care about. And or maybe you prefer to think of it this way, which I do, is that isn't this height change the distance we actually care about? Maybe something like that. Okay. And isn't this height equal to here? I'll write it two ways. It's L times what or L times what? Okay. If you're bouncing off the 30-degree angle that the book gave you, it's L times what? Sine or cosine of 30 degrees? Sine of 30 degrees. You can see how it's like flipped over opposite, right? And then vice versa here, cosine of 60 degrees. Okay. This is the same thing. If you ever have two angles that add up to 90 degrees, like here, then the sine of one is equal to the cosine of the other. So it's the same thing. Let me prove that to you guys real fast. Sine of 30 degrees is 0.5. Cosine of 60 degrees, 0.5. It's the same thing. Okay. But if you're really curious about what I just said, let me write that over here. Okay. So if you have sine of some angle, okay, versus cosine of 90 degrees minus that angle, those are the same same value. Okay, so back to here. I know that the force is probably something to do with her weight, right? So m times g. Okay. And that distance is the height change. But that height change, if you want to do the cosine as the book formula, you have to bounce off the 60-degree angle. Okay. If I want to do the bounce off the given angle, which is 30 degrees, I actually have to use the sine version. Okay? So whether you're using sine or cosine, be careful as to what the reference angle is. Okay? So her mass was 60 kilograms. She's in a gravity field of 10 meters per second squared. Okay? Remember, the book did not tell you 10 meters per second squared. They would assume that you would pick up on that and know to apply that. Okay? The distance, the full distance she went was 200 meters. That's L. But only a component that actually matters. The only part that matters is the height change. Okay? You guys see how L sine theta is height? Hey, that would be mgh, wouldn't it? Mgh. Maybe I should put that here as a middle step. So sine of 30 degrees. Okay? Where sine of 30 degrees is a half, because this height is half of this length for this 30-degree angle. So what is 600 Newton weight times 200 meters long, but only the sine of 30 degrees actually raises her that height. Okay. I'm looking at 60,000, and what's the unit on this again? Joules. That's how much work was done. Okay. Okay. So whoever's running this escalator, they had to buy this much energy from the electric company to make that happen. Okay. You might also call that 60 what? Kilojoules. Good call. 60 kilojoules. Guys, go back. Oh, we've got a graph one. Number 78. The graph shows force and displacement for an object being pulled. Let's take a look at this graph before we get into the question. Okay. So force versus displacement. In your notes a few days back, I gave you guys two graphs, and they were both had the same sets of axes, force versus distance. Maybe shot for those. Okay. You guys remember before last week, most of the graphs we deal with have a time axis on the horizontal axis, okay? But not this week. We're using displacement, so force versus displacement. In fact, whenever you see force versus displacement in a physics textbook, it's probably going to be a work or energy question, because what property of a force versus distance graph tells you work? The area under the curve, right? Could be newtons times meters, or something to do with that, which would be joules. Yep. Right. Let's take a look at the question. Calculate the calculate the work done. That's exactly what they're asking. To pull the object 7 meters. Now, a little bit tricky right there. See, 7 meters. You guys do see that that's not actually the full graph. It only stops right about there. So, a little trick right there. Okay. So, what is the area under that curve? Now, I'm using the term curve in a math sense. Right? So I know it's all like jaggedy. Right? It's not all curvy, but. Right. So the way I would approach this is to break this into shapes. You guys see what I did here? So this is a funny looking shape. Well, I got a triangle next to a tall skinny trapezoid, which I can further break into a triangle and a rectangle. Okay? And there's a big old rectangle right there. That looks like where probably most of the work was done during that constant force section. Okay. All right, let's tackle that. Okay. So the work done for number 78 work is equal to, right? Well, we need to add up 4 bits because I see 4 shapes. Right? The first one's a triangle. Isn't the area of a triangle 1/2 base height? So I see a base of 2 meters. 2 meters. I'll just go ahead and use the textbook numbers for this question. Okay. And a height of 20 newtons. So there's the area of that little triangle, that first shape. Right? That represents the energy to do that part. Right. Then there's a small rectangle here with a base of 1 meter and a height of 20 newtons. So base times height is a rectangle. So for the area. So a base of 1 meter and a height of 20 newtons. Okay. But then there's a triangle sitting on top of that. So another 1/2 base height for a triangle. Same base of 1 meter. Okay. What is the height of this triangle? How many newtons? What's this 50 minus this 20? 30, yeah. 30 Newton tall triangle. Right. And then one more shape. That's the big old rectangle. But remember, stop at the 7-meter mark, because that's what they said to do in the question. Okay. So that's a base of, what base is that? Yeah, 4, because it goes from 3 meters to 7 meters. So it's a base of 4 meters. And a height of what? 50 newtons. There you go. Okay. Piece by piece, that looks like 20 joules plus another 20 joules plus half of 30 is 15 joules plus 200 joules. 220, 40, 55, 255? 255 joules of work. We're done moving our object. Okay, all right. Well, that was part A. Part A, what was the work done? Part B says calculate the power that would be developed if that was all done in 2 seconds. Right? The power. So part B, power. What was the formula for power? It's what for what? It's like work per time, right? Remember, it's like a rate of work. Okay? So it's like work per time. Do you guys remember what the unit for power is? Watts. Yeah. And you're probably familiar with this by looking at the top of a light bulb. It might say like, this is a 20-watt light bulb. Ah, that's right, because that's the rate that it pulls energy off the grid, right? Energy per time. If you have it plugged in right now. Okay, like that. Okay. So we're looking at 255 joules of work, all done in 2 seconds. Oh, well, that's easy. If you do 255 joules of work, all in 2 seconds, that looks like 127 some watts. Hey, that's kind of like a 100-watt light bulb, isn't it? Pretty close to. Okay, so if you have this machine, say this is a machine, maybe you have it hooked up to the grid, and it can draw like 127 watts, then it could do this task in 2 seconds. Guys good? Okay, number 81. A pulley system lifts this weight, this distance. So like a height change. Paul pulls a rope a different length, right? Exerting a force of a much smaller force. I see he's pulling a lot of rope compared to the height change, but with a very small input force. Oh, this is what you guys did yesterday. You guys spent all day yesterday in here just constructing these pulley systems. Oh, and look at the questions. What's the ideal mechanical advantage? And then what's the, well, they say mechanical advantage. I think I was calling that actual mechanical advantage or real. Right? And then they ask a question about efficiency. All right. So, where's, you guys remember all day yesterday, I had this on the screen. You guys remember this? Okay. So, think about this real fast. I'm showing a 3-to-1 mechanical advantage system here. Okay. And you can figure out what the mechanical advantage is, I should say ideal mechanical advantage, by looking at the geometry of this thing. So you guys see this movable pulley, right? There's 1, 2, 3 ropes up for that 1 force down. So it's like the force gets split into 3 different ways. Okay. Or you guys can see the live version right over here. You guys see 2 fixed pulleys there and a movable pulley right here, moving up and down with the weight. Okay. Just like you did yesterday. Okay. Then ideal mechanical advantage is just playing off the geometry, the ratios of distances. So you pull some string here and this moves up some distance. Those are different distances, right? But the ratio should represent the mechanical advantage. Right? It should be like 3-to-1. Right? But then there's actual, like real mechanical advantage. The whole point of mechanical advantage is to amplify your strength. So what's the ratio of the forces? And that might fall a little bit short of the ideal because there might be some frictional forces, maybe something like that. Okay? And efficiency is just, well, what if you compare the two? What is that ratio of those different perspectives on mechanical advantage? Okay, so that's what we're about to do right here. Now I'm gonna make up my own pulley system. I know they didn't give you guys a picture on this one, so I'll draw you guys a picture. Got a ceiling, Let's get a couple of fixed pulleys. Fixed pulleys. Maybe there's a movable pulley. Actually, I'm gonna make this movable pulley a double pulley, just like you guys remember those double pulleys you had access, or you guys can see it right here. You can see the slide version, two wheels side by side, right? And let's take a spring scale, hook it to the string. It's gonna wind around this one, down underneath one of these. Maybe up through this one, over here, back underneath the other wheel, and then hook it right here, something like that. And then from this one, I'm hanging a little lab weight, like that. Okay. Now, what I just drew, you guys, can you guys look at that geometry and tell me what the ideal mechanical advantages of that system? Who sees it? What's the ideal mechanical advantage of the one I just drew? So here's your movable pulley. How many strings do you see going up? See 4? Hey, so it's kind of like this weight gets split 4 different ways. Do you think this is a 4-to-1 mechanical advantage? Okay. It should be. Right, so let me give you guys some numbers. I'm going to call this weight 1,000 newtons. The next number your book gave you was the height change of it. So let's pull this up. A height of, I'll say 10 centimeters. The next number they gave you was the distance that Paul pulled the rope. So, oh, now this distance right here, there's only one number I can even write. So distance pulled. What's the only number that can go right here? If it's 4-to-1 mechanical advantage, when it lifts something 10 centimeters, you have to pull how much string? Yeah, 4 times 10 is 40 centimeters, right? So he pulls 40 centimeters for this thing to move up 10, right? Now, if this was 100% efficient, he would be pulling with how many newtons of force? What's 1,000 divided by 4? Yeah, 250 newtons, right? So if this is not 100% efficient, then shouldn't the pulling force be, well, maybe a little bit more than that? So I'll say F pull is, I'll call it, let's go 300 newtons, and we'll figure out from there. Because it has to be at least 250, but it's probably realistically going to be a little bit more than that. Guys good? All right, so your book gave you basically those 4 numbers, and I'm giving you guys a picture to go with it. So part A, what is the ideal mechanical advantage? Can I zoom out here? How much? Maybe I'll put that right here. Part A, ideal mechanical advantage is the ratio of the distance pulled compared to the height change, which is, on my picture, 40 centimeters compared to 10 centimeters. That's a 4-to-1 mechanical advantage. Okay. And for your guys' textbook numbers, whatever those 2 distances are, they should work out to an integer value. Like I got an integer value, I got 4. Did you guys, how many of you guys tried the book numbers and got an integer value? Did you guys get something like that? Right. But then the part B says, well, what's the real mechanical advantage? Say the ratios of the forces. So like real mechanical advantage, well, that is output force compared to input force, which is the weight compared to the pulling force. So this thing weighs 1,000 newtons, and he's lifting it with only 300 newtons of force. Ooh, definitely getting a mechanical advantage. But if you divide that out, it should be less than 4-to-1. Let's see, what's 1,000 divided by 300? Yeah, it's like 3.3-to-1 mechanical advantage. Okay. And same story for your textbook numbers. Whatever the real mechanical advantage is, should be less than the ideal. Oh, well, just enough time to finish. Last question. What's the efficiency? The efficiency of the system is the actual mechanical advantage, real mechanical advantage, compared to the ideal mechanical advantage. Guys, what's times 100%, right? Guys, what's the biggest number that this could possibly be? About 100%. If it was 4 to 1 here, 4 to 1 here, that would be 100%. Okay? But in this case, it looks like it's 3.33 compared to 4. What is that? 83%. So my number is showing 83% efficiency. And then your textbook value should be, well, I don't know what the answer is, but it's probably something in that ballpark, maybe 90%, maybe, well, it should be less than 100%. Okay, what questions? All right, we got 30 seconds to the next weekend. So that is a good pause point right there.